The topic tonight, as you can see, is heat. I mean, there are people out there who think the universe actually runs on peace and love, man. But in actuality, it's heat. Right. Number of topics to work through tonight. There is inevitably in a subject like this a certain amount of physics. So we start off by trying to understand the nature of heat and temperature. Then we'll move on to think about the Big Bang and the temperature of the universe. And then I want to move into a subject called thermodynamics, which you may or may not have come across before. It's the study of energy and energy transfer. And a look at that to see how it actually fits into our model of the universe. Heat is a form of energy. Energy comes in a variety of forms. Ones that are most used to things like kinetic energy and potential energy. Kinetic energy is motion, is moving. Potential energy comes from we have according to Einstein, as I'm sure you're aware, energy and mass are different manifestations of the same thing. So we have rest mass, which is associated with mass. That's a form of energy as well, in the form of mass. We have chemical energy, which is stored in the bonds between atoms. Electrical energy, which of course you're used to, which is the movement of electrons. There are certain materials where the electrons can move freely through the atomic matrix, and we call them conductors. That's electrical energy. And then heat. One of the principles of energy is that it can be neither created nor destroyed, but is merely transformed from one form to another. And a good example here, if we go back to kinetic and potential energy, if you stand at the top of a cliff with a stone in your hand, the stone has potential energy compared to the bottom of the cliff because it's above the bottom of the cliff, so it's a height above it. As you throw the stone off the cliff towards the ground below, towards the beach, so it gets closer to the beach, so it starts to lose potential energy, but it starts to gain kinetic energy because it's traveling faster and faster. It gets to the bottom of the cliff, it's lost all its potential energy, but all that potential energy has been transformed into kinetic energy from its motion, except that now it comes to a sudden stop. But that kinetic energy has to go somewhere, and it's actually liberated as heat. You'll find the stone will be just that bit warmer at the bottom when it's hit the ground than it was at the top. And that's the energy being liberated, again, being converted into heat. So you don't create or destroy energy, you simply move it from one form of energy to another. We're concerned today with heat. And it's a form of energy. We can transfer it from one body to another. And it raises the temperature of the body that it enters. And as it relieves the body, so of course it reduces the temperature of the body as well. There's one characteristic about this flow of heat from one body to another, and it always flows from a hotter body to a cooler body. No one has ever witnessed it flowing from a cooler body to a hotter body. If you think you can do that, please go ahead and try, but no one's ever actually managed it before. It's often a byproduct of many processes. We often have mechanical energy, say in your car, for example, is doing work, and it's doing work against friction, say, and the end result of the mechanical energy, which may be converted into kinetic energy in the car as well, is it finishes up as heat again. The problem we have is if we try and transfer that heat back into mechanical energy, we can't get 100% efficiency. If we try, I mean, the car engine, for example, the internal combustion engine, yes, we get kinetic energy from it by making the car move forward, but a lot of the heat that we generate in the engine is rejected into the atmosphere through the exhaust, through the bearings, the transmission, the brakes, and so on. It's not a very efficient way of doing it. So we have this problem of converting heat back into mechanical energy. It does raise the question whether there is a natural inclination for all energy to eventually turn into heat. I have a strong suspicion that is actually going to be the case. I can't prove it. There's a lot about heat we can't prove, but I suspect that's the way it's going to go. I wouldn't worry too much. We are talking hundreds of thousands of billions of years, so I wouldn't worry too much about it yet. Excuse me. At the microscopic atomic level, when we're talking about temperature, we're talking about internal energy of an object. And this is the average kinetic energy internal to the object. In a solid body, something solid, The atoms are bound into a matrix, but they vibrate within the matrix. And the more energy they have, the more they vibrate. The bonds between the atoms act as a sort of a spring. So this is the internal energy. And the more they vibrate, the more kinetic energy they have, the more heat they have. In a fluid, and the fluid includes liquid or gas, you have this random motion of molecules around the liquid or the gas, and the more they move, the faster they move, the greater distance they cover, the greater the kinetic energy, again, the greater the heat. We've talked about flow from one body to another, and it's this transfer of internal energy, this kinetic energy of the particles in the material is transferred from one body to another. That's how heat flows from one body to another. We'll look at that more carefully in a moment. Okay. So here we have a couple of pictures. The first one is a fairly cold object. It's a solid, so the particles are vibrating. As we heat it up, so we get bigger vibrations of the particles, what's happening here is they're actually taking up more space. The atoms are taking up more space. The mass is no greater, but they're moving around much more within the matrix. And it's this movement which causes the object to expand, if it's metal, for example, but also because they're taking up more space, but they're not getting any heavier, the mass is still the same, the density of the material actually, or the atoms actually decreases. Density is mass over volume. The more they're moving around, the more space they're taking up for the same mass, the less dense the object. And that becomes an important point later on. Heat and temperature are not the same. If you put a pot of water on the stove, the temperature goes up. Okay, you put in more heat, more temperature. It's just they are the same. But unfortunately, well, not fortunately, but you know, they aren't. The temperature is a reflection of the kinetic energy of the particles, how fast the atoms in the substance are moving, or the molecules. Temperature is a measure of how many particles there are in a substance, multiplied by how much energy each atom possesses. So temperature is just an indication of how fast the atoms are moving. Heat is a measure of the density, if you like, of the material. Home experiment time. You can get 2 pans, fill them with the same amount of water, and cover them up and put them on the pan, on the cooker, and turn the ring on full. Heat them both for the same amount of time. They both receive the same amount of heat, but you'll find they are at different temperatures. Okay. It's a question. Which has more heat, a flame or an ice cube? Anybody like to suggest an answer? Anybody? I'm not. Sorry? Flame or an ice cube? Flame?
Depends on how big the ice cube is, isn't it?
You tell me. Is that an issue? I mean, I'm just picturing an ice cube there, it's normal size.
I assume a flame.
Yeah, okay. Unfortunately, it's not. There's actually more heat in an ice cube. The atoms in the ice cube are moving about 3 times slower than the atoms in a flame. So each atom has lower kinetic energy. But there's about 1,000 times more atoms in the ice cube than in the flame. So although the temperature of the flame is higher, the heat is greater in the ice cube. Is everybody with that? If you're not sure about this, there's another experiment you can try later, provided you've got well, when you finish, turn your oven on for a while, up to say 300 degrees. When it's up to 300 degrees, open the door and put your hand inside. It feels warm. I'm sure you've all done this. It feels warm, but it's quite, no problem at all. Now grab hold of one of the shelves or ram your hand against the side. When you stop screaming, consider what's happened. And what's happened is that The air inside the oven and the sides and the shelf are all at the same temperature, but the number of particles in the air are far fewer than in the metal shelf or the side of it. So there's a lot more heat in the metal than there is in the air. So the air, the same temperature, but much more heat, if that makes sense.
Okay. How is heat measured then? Is heat measured in degrees, isn't it?
Yeah, I'll come to that in a second.
Oh, okay.
Yeah. I must admit, it's proven quite difficult. I've got no feedback from anybody about whether people are following me or not. It's actually quite difficult, this.
I suppose, actually, Paul, that's why when we got a new quartz worktop, they were saying, whatever you do, don't put a hot pan on, boiling water. And I'm thinking, well, hang on, if the water can't get above 100 degrees, the heat, therefore, should be the same on both. But actually, the temperature's the same on both, but there's more heat in the pan, and that's why you don't put the pan on, but you can pour boiling water on it without damaging it.
Yeah, that makes sense. Yeah. So, all right, great. You've understood what I'm talking about. That's great. Thank you. Okay, we'll move on. This question of how we measure temperature and heat. Heat is measured in joules. Heat is energy, and the unit of energy is the joule, and it represents the total energy of all the molecular motion inside the object. Putting it into everyday terms, my background is mechanical engineering, so looking at it in terms of classical mechanics, energy is defined as work done, where work done is force times distance. So a force of 1 Newton acting through a distance of 1 meter uses 1 joule of energy. Okay? Obviously, using different forms of energy, different ways of measuring it, but in terms of classical mechanics, and you can see for the diagram there with the horse and the coal wagon, the horse is applying a force moving the wagon through a distance, and that's so much energy is being used, and it's the force. So sometimes instead of using joules, some people you call it Newton meters instead, which is force times distance. The joule is an SI unit, but a fundamental unit because it's derived from other units. Temperature is measured in degrees, normally in everyday life, Celsius, degrees Celsius or centigrade, where the SI unit is the Kelvin. And I made the mistake, I'm sure everybody else does, it's not degrees Kelvin, I had to change it, it's just Kelvin. It's degrees centigrade or Celsius, but just Kelvin. And temperature is just the average heat or thermal energy of the molecules in the substance. It indicates the work can be done, but doesn't give an indication of how much, because it doesn't take into account the number of particles, the amount of kinetic energy. It just indicates that the average kinetic energy within the object is proportional to heat, because if you give an object heat, you get a higher temperature, and if you give a larger object the same heat with a lower temperature, there's some measure of proportionality there, but it's simply an indication that work can be done rather than an indication of how much work can be done. We have 3 ways of transferring heat: conduction, convection, and radiation. The sun is a source of heat for our planet, as I'm sure you're fully aware. Depending on the size of the star, actually, but stars have conduction and convection both going on within them, but in different parts of the star, depending on the size. But nevertheless, the heat from the core comes up through the star itself by a mixture of conduction and convection to the surface, is then travels through space in the form of radiation. It then reaches the Earth, and then it's transferred around the Earth again back by conduction and convection. You can see there in the picture at the bottom, we've got the rather archaic looking boiler that's actually using all 3 forms of heat transfer there. You've got conduction to the kettle, convection is keeping the cat warm, and radiation is keeping the man warm reading the newspaper. We look at conduction, first of all. We've got these atoms vibrating in a solid mass. And heat is transferred through the material because there's a contact between the atoms, and so some of the kinetic energy is transferred to the next atom in line. And that in turn contacts the next atom and transfers some of the energy to the next atom as well. So the kinetic energy gets spread through the material. But of course, we can't create more energy. So as you move the energy through the material, so the original atom loses some of its own energy. The atoms don't actually move out of position. It's just this knocking together, if you like, of the physical contact between the atoms. In the same way, the bottom diagram there, you've got the higher temperature and lower temperature side. That could be the high temperature could be your mug of coffee, the lower temperature could be the room, and the surface could be your mug. So you have the higher temperature, you have molecules with higher kinetic energy in the mug, dashing around all over the place. They're hitting the side of the mug, so they're transferring some of their energy into the atoms in the mug itself. The atoms in the mug knock onto the other atoms in the mug, which knock on the other atoms in the mug to the outside of the mug. And then particles in the room, molecules in the room, where it's cooler, come into contact with the surface, and some of the kinetic energy from the mug surface is transferred to the air molecules. And so there's an increase in temperature in the room around the mug. So the mug gets cooler and the room gets slightly warmer. And that's conduction. It requires a physical contact between objects. There's a couple of examples here. The top one again, you've got I'm sure you're familiar with Newton's cradle. That's a variation on the theme, I think, at the top there. But you can see how as each pair of boys hits the other pair of boys, so the kinetic energy is transferred from one to the other. And again, the same thing at the bottom with the kittens playing with Newton's cradle again. As the balls hit, these are the molecules, so the energy is transferred to the next particle, next ball in line. Convection. I said before that as you heat something up, as it becomes more, as the particles become more energetic, they take up more space and they become less dense. Because they become less dense, they tend to rise. Where you've got a liquid or fluid, they can rise through the fluid because they're less dense than the colder fluid around them. So as they rise up, they tend to cool down. As they cool, so they tend to contract again, become less energetic, and so they start to sink. And what you can set up in a liquid or a fluid, as you can see, there's some convection cells. That's actually a cut of the surface of the Earth bottom there, and you've got a couple of convection cells. So that they're heated by the core, and so they expand, the density drops, they rise up. As they rise up, so they start to cool, so they drop down again, allowing other hot particles to rise up behind them. Two requirements here: you need gravity. You can't get convection in a weightless condition. The other picture there actually shows the surface of the sun, and again it's showing a series of convection cells where under the surface there you've got the rising of hot gas and the dropping back down again of cooler gas. But those cells I think are around about 6,000 kilometers across, if I remember rightly, typically that size of California, I think. But you get this off a radiator in a room. Where the hot air rises from the radiator, flows around the room, sinks back down again. But in the meantime, other hot air is rising off the radiator behind it and following it around. And the cool air is coming in to replace the hot air that's risen, getting heated by the radiator, and then rising up again and following it. So you get the convection cell within the room from the radiator. The third method is radiation. And here we're converting it into electromagnetic energy. People often call it light, but of course it's a whole range of electromagnetic radiation. Radiation like this can be either as a waveform or as a photon. And we consider photons are packets of energy. The energy depends on the wavelength of the photon, and it goes all the way from gamma rays up to radio waves, the whole range of electromagnetic radiation. What photons can do, first of all, they can travel through space, which is useful, what we're using them for. If you remember, they're transferring the heat from the sun to the Earth. So they're getting the energy levels, they're being ejected, if you like, from atoms. So the energy level of the atom is dropping as it ejects the photon, which is taking some energy away from it, travels through space, comes to the Earth, and then it can change the energy level of an electron, an atom. And in fact, we know this because this is the kind of effect that gives us the light and dark lines on a spectrum, which we're all familiar with. We can use it to ionize the atom. I say we can use it. It can ionize the atom. It can cause the electron to break free from the atom. But it can also increase the kinetic energy. It's a packet of energy, and if it's absorbed by the atom, it increases the kinetic energy, and so the atom appears to be hotter. Remember, what we feel as heat is kinetic energy. Very briefly, the electromagnetic spectrum, we have radio waves at one end. It's gone up to 10 meters. I believe, if I remember rightly, that a radio can go up to kilometer wavelengths, actually. And we move along down through the visible to gamma rays at the end. Very short wavelengths and very high energy. Radio is much longer wavelengths, much lower energy. And we can express this in other terms of frequency or energy. I'm sure we're all familiar with this, so I'm not laboring the point here. So, I want to move on to the Big Bang now. We talked a bit of theory. Let's try and apply some of this. I want to start off with this concept of what's called a black body. Anything above absolute zero emits electromagnetic radiation. That includes you and me. We're all emitting radiation in some form. We have this concept of a black body. And a black body is a perfect emitter and absorber of radiation at all wavelengths. If it didn't emit and absorb all wavelengths equally, it would either heat up or cool down. So it's actually a thermal equilibrium. If it's low enough, if the temperature is low enough, then it is black. But a lot of black bodies aren't that cold. Oddly enough, a star is an approximation to a black body. Spectrum from a star, within the black body spectrum, there's a particular form of spectrum that we get from a black body. It's a smooth function, and all black bodies emit spectrum of the same shape, but the particular characteristics of the spectrum will tell us the temperature of the emitting body. So we've got here some spectra taken from different stars. The big diagram at the bottom, for example, you can see there at the top one is a star at 600 Kelvin. We'll define Kelvin later, don't worry about it too much for the moment. A degree in Kelvin is a degree in centigrade. The difference is 273 degrees. We'll worry about it later, but suffice to say that we've got a range of stars there with surface temperature 6,000 Kelvin, 5,000 Kelvin. You know, as the stars get cooler towards the bottom of the diagram, so the peak shifts to the right. And what it's doing is moving towards the lower energy end of the spectrum. You'll notice, incidentally, one curiosity about this diagram, you notice that you've got the visible region, the visible part of the spectrum there. And you'll notice also that there is the orange-yellow part of the spectrum falls somewhere between 5,000 and 6,000 K. The sun is reckoned to be about 5,600 Kelvin, so it falls more or less snap bang. So the peak output from the sun will be in the orangey-yellow region. What it suggests, I've never seen it proved, but what it suggests is that we've actually evolved under the light of the yellow star, and our visible region is actually the peak output of the sun. The sun peaks, the output in the spectrum peaks in the yellow part of the spectrum, and that's where we see either side of that as well. If we evolved under a star of, say, 3,000 Kelvin at the bottom there, our visible region would be somewhat different. And you can see at the top there as well, diagram, looks at some hotter stars 9,000 Kelvin, 12,000 Kelvin, where the peaks actually moved out of the visible range. The important thing about these spectra is that we have what we call Wien's displacement law. And if you identify the peak wavelength, so for example, for 6,000 Kelvin, it's probably about, I don't know, 500 nanometers or thereabouts. The temperature is the star is 0.0029 divided by the peak wavelength in meters. It's actually quite straightforward. And if you can get the peak wavelength from these diagrams, you get the temperature of the star. And that's where they got the temperature from. So these are black body curves. All stars put out curves of this shape. As you can see, they're all the same shape, same basic shape, just some are taller and shifted to the one direction or another. So they're black body curves. The Big Bang itself, 13.7 billion years ago, started at time 0. Temperature was probably infinitely high. I'm not quite sure whether that's quite right, but we'll let it go. And it had 0 size. And then it was a singularity. It was a single point. I can't say in space because it wasn't in space. Space didn't exist at the time. Space-time didn't exist. It was created with the Big Bang. But there's a singularity somewhere. It exploded and time started. As you can see, the temperature started to drop quite rapidly. At 10 to the minus 43 seconds, which we call Planck time, a time we cannot go any earlier than that, our physics doesn't do that, temperature dropped down to 10 to 32 Kelvin. So we've gone infinitely high. To 10 to the 32 is 1 followed by 32 zeros. That's quite large. There was a period called inflation, which started at 10 to the minus 35 seconds. 10 to the minus 35 is 0.34 zeros and a 1. So it's still quite early on in this life of the universe. The temperature dropped quite rapidly, as you can see. But inflation was a period when the universe expanded much faster than it should have done. And there are reasons for this. I'm not quite sure what they are offhand. It didn't last so very long, but it grew rapidly from fractions of a meter to a meter. By the time we got to 1 to the thousandth of a second, the temperature dropped to 10 to the 13 Kelvin, which is 10,000 billion Kelvin, so it's getting quite cool by then. And time goes on, you get to a second, it's dropped down 10 to the 10, that's say 10 billion Kelvin. It's getting quite cold now. At 100 seconds, it's gone down to a billion Kelvin. 380,000 years, we're down to 3,000 Kelvin. That's quite an important time. Still quite young. We don't give them the size anymore. That's a period called recombination. And what happened here is that the temperature is sufficiently low now. Before this period, the temperature, the energy in the universe, the temperature, the heat, was sufficiently high that it prevented electrons joining up with protons. So we had this sea of protons, a sea of electrons. If they tried to combine, there's sufficient energy to break them apart again. By the time we got to have 380,000 years, what we call recombination at 3,000 Kelvin, the temperature dropped sufficiently low, which allowed protons rather, and electrons to combine to form atoms. That's the beginning of atoms. One of the issues of having electrons is that they stop photons flowing through the universe. They were blocking the photons. They were deflecting the photons. Because the electrons were now starting to be tied up or bonded into the into the proton to form atoms, the universe actually at this point became transparent, and for the first time, light actually flowed through the universe. I say light, electromagnetic radiation is probably a better phrase. It probably wasn't light. I mean, light is only light because that's what we love to see. So, okay. So temperature is dropping. We get to 13.7 billion years, where we are now. We're down to 2.725 Kelvin. That's nearly minus 270 centigrade. The universe itself, size is now grown to 10 to 27 meters. That's billion meters, so it's getting quite big. But you can see how the temperatures, as we go through the life of the universe, temperatures drop down and down and down. It started infinitely high, has some extremely high temperatures in very early fractions of a second, but now we're down to, well, we're not quite sure what it is. I mean, it may be, we'll find out in a minute. You're familiar with the concept of red and blue shift. Something moving away from you has a red shift, something moving towards us, light moving towards us has a blue shift. We're all familiar with this concept. But you've also got gravitational red and blue shift. And photons, if they're traveling out of a gravity well, lose energy. And so they tend to red shift. If they're moving into a gravity well, so when they're moving towards the Earth, for example, they tend to have a gravitational blue shift, something that was first identified by Einstein in 1907. You've probably seen this picture before. It's taken by a probe called COBE, the Cosmic Explorer, Background Explorer, first of a number of probes to measure background radiation, followed up by WMAP and by the European Space Agency's Planck. What it actually shows is the temperature fluctuations that existed in the early universe. At around about 380,000 years, when I talked about recombination just now, when radiation could flow through the universe, you might think at that point that the radiation would be at an even temperature. It's all come from the same source, from the same Big Bang. But in fact, as you can see, there are fluctuations here. There's some blue, most little blue fluctuations, and some red as well. These represent changes in temperature. We're talking about microkelvins, so they're very, very tiny. But what they represent are gravitational fluctuations in the universe itself. So what you've got here is the beginnings of stars, of particles coming together, things like protons coming together, slightly increasing the gravity in that area, and with the gravitational red and blue shifts, we can see that quite clearly embedded in the sea of in these images taken by COBE. So what we're seeing here, 380,000 years, are the beginnings of things like stars and galaxies. It's the original blueprint the light. It's actually in the microwave range now. That's why it's called microwave radiation. And it uses the temperature of the universe, which is 2.72548 plus or minus 0.00057 Kelvin, or approximately 2.73 Kelvin, or minus 270.42 degrees centigrade. How the hell they got it so accurate, I have no idea. I'm guessing personally. But nevertheless, it gives us the temperature of the universe. As I say, the differences in this diagram, there are differences because of gravitational red and blue shift, but the differences are in microkelvins, minute changes in temperature. I'm coming to the bit I'm not happy with. I have to admit, I spent the last 2 days trying to work this bit out, so please bear with me. The temperature of the universe. If you take a very precise thermometer into space and you stick your hand out the window with it, space itself isn't actually a pure vacuum. A lot of people think it is a vacuum. It isn't. There's dust and gases, ionized particles from the sun. It's very, very tenuous, very, very thin. There's lots of space between all these particles, but nonetheless, space isn't actually completely empty. We've talked about heat in the context of kinetic energy of particles. But if you stick your arm out the window with this thermometer, it's highly unlikely that any of these particles that are out there, they're so thin and so few and far between, it's unlikely they'll bump into the thermometer. So they're unlikely to impart any heat from themselves into the thermometer, or the thermometer to impart any heat into them. If they do, it'd be pretty cold. So between the particles, you have a vacuum. It's devoid of any baryonic matter. Baryonic matter is matter as we know it. What will happen is the thermometer will start to lose its own heat, to start radiating away heat as electromagnetic radiation. and it will continue to drop until it reaches a temperature of 2.3 Kelvin, which we just talked about. This, again, the temperature we found from COBE and from the other probes that we sent up to measure the cosmic microwave background radiation. So it raises the question, what determines the temperature of the universe? There are a number of factors here. I've looked at a number of articles on this section, and each one gives me a different answer. So please bear with me while we try and work through this. And I'll try to simplify it as much as I can, more for my benefit than anybody else's. Really, if we look at the temperature of the universe, there are two options. Okay, we can either look at the light from current astrophysical objects like stars and galaxies and so on, or we can look at the light from the Big Bang. We need to decide which one of these is a better measure for the background light from the universe. Okay, so which explanation fits better? If we look at the leftover light from the Big Bang, the microwave background radiation we just talked about, what we find is that the spectrum of light that we see is a perfect black body spectrum. The universe would appear to be a perfect black body, odd that may sound. If we look at the light emitted from astrophysical objects, yes, they're also emitting black body spectra, but each one is emitting its own spectra. So we get a much more, perhaps blurred, not quite so sharp spectrum. It's not such a good, the curve that we generate from all these different black bodies isn't as perfect as the one we get from the Big Bang, which suggests that the light from the universe is the most perfect black body ever observed. So the light from the Big Bang, the cosmic microwave background radiation, will suggest that is the light that we use to measure the temperature of the universe. It seems to be the best fit to what we're trying to do. Here we have the black body spectrum for the cosmic microwave background. And as you can see, it's peaking at about 1 millimeter in wavelength, right up into the microwave part of the spectrum. If we use Wien's displacement law, if we, for example, if we use 1 millimeter, it's not quite 1 millimeter if you look, it's actually slightly off, but if we use 1 millimeter, and we put it into Wien's displacement law there, 0.0029 of the peak wavelength in meters, well, that's, if we use 1 millimeter, that's 0.001 meters, that actually gives us a temperature of 2.9 Kelvin. That's not far off. I mean, it's not quite 1 millimeter anyway, as you can see. So from this curve, and Wien's displacement law there, we can get, again, this is how we arrive at the temperature of the universe. Using the cosmic microwave background radiation and this black body curve, we get a temperature of 2.74 Kelvin, just above very, very cold. It does raise the question, where's the energy gone? Again, as I said, I was trying to read up on this the last couple of days, and I keep, every time I look at something, it gives me a slightly different explanation. So really what I've done is pick 2 or 3 of the explanations, put them down here, and I'll be quite honest, I have no idea what it all means. I was going to say that, of course. Okay, so what's happening as the universe expands, the first radiation is redshifting because it's expanding away from us. Photons that are redshifted have a lower frequency, a smaller wavelength, rather, and so they exhibit lower energy. The expansion also slows down matter particles. So again, they have reduced energy and therefore reduced heat. So where has the energy gone? The box on the right shows you what the universe is made of. And you'll see matter. About 95% is dark matter and dark energy, which we don't really know what it is. It would appear, I mentioned at the beginning, the conservation of energy, you cannot create or destroy energy, is actually a local statement. It applies in a small area, but not on cosmological scales. Cosmological energy is non-local. And the problem we have is that we can't find total cosmological energy, because 95% is dark matter and dark energy, which you don't know what it is. And so it can be argued, if we don't know, if we can't define the energy, we can't actually formulate conservation laws for something that we can't even define. So the answer is we don't quite know what's happened here. Another argument put forward is that energy is only conserved when the laws of physics don't depend on time. In the view, the universe does change with time, and the laws of physics change with time. We saw from the Big Bang that Planck time at 10 to the minus 43 seconds. And the problem with that is that our laws of physics don't go back beyond that time. It's a very, very tiny portion of time, but the laws of the universe changed at that point. So the universe did change at that time. There are other changes as well, where, I mean, the initial universe was more or less pure radiation. That changed over time to become the normal matter that we have now as well. And the universe does change over time. So it does suggest maybe the laws of physics, maybe again, you know, as with the first statement, we can't apply our local statements to the cosmological scale. The red shift actually represents a photon moving away from the observer. That's because us as the observer, if you like, are standing still, and the photons are moving away, so we see the red shift. If we were moving with the photons, we wouldn't see a red shift. We see the original wavelength. So it does suggest also that it's not so much no loss of energy, it's just that we're detecting the energy we're detecting is different. The energy is still there, just that we can't see it because of the redshift. So you've got a number of different statements here. I don't know which one is right. I'm not that good, frankly. Maybe we can discuss it afterwards. I think we'll move swiftly on at this point. Right, thermodynamics. Arnold Sommerfeld came up with a good definition of it. He said it's a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for one or two small points. The third time you go through it, you know you don't understand it, but by that time you're so used to it, it doesn't bother you anymore. As a student, I spent 3 years studying thermodynamics. Believe me, that's true. It really is. It's the weirdest subject I've ever studied. That's why we're going to do some of it tonight, I think. There are 3 laws we're going to look at tonight. This is the 0th law because they discovered it after the first and second laws, and it actually belongs in front. These laws are in the main blindingly obvious, particularly when they're pointed out to you. But you can't deduce them logically. We can only see them, find them by observation. And as I said earlier, if you know, with this question of heat flow from cool to hot body, if you want to try and prove that, go ahead. But no one's ever managed to do it so far. The 0th law: if 2 objects are in thermal equilibrium with a third object, then all 3 of the objects are in thermal equilibrium with each other. So what it's saying is, if A and C are in thermal equilibrium, and B and C are in thermal equilibrium, so A and C are the same temperature, and B and C are the same temperature, then A and B must also be the same temperature, even though they're not touching. There's no logical way to use this. You can see it's obvious when we look at it that way, but you can't actually prove it without actually observing it. But what it does do, it allows us to define temperature scales. The Celsius scale, one we're very familiar with, we probably know where it comes from. We take 2 fixed points, the melting point of ice, which we assign a value of 0 degrees centigrade, and the boiling point of water, which is assigned 100 degrees centigrade, at standard atmospheric pressure, which is what we're in at the moment. And then we divide the region between into 100 intervals. The usual thermometer, again, you will know, uses mercury. Some of the clinical thermometers, I think, use alcohol. There are other ones you can use. There's an example there of a temperature-sensitive resistor connected to a fixed voltage source. So you put a voltage through a temperature-sensitive resistor. The resistance changes according to the temperature, and an ammeter connected to the circuit is then calibrated to read, instead of the change in amps, it's calibrated to read the temperature. It's fairly straightforward. So that's a Celsius scale. But of course, in astronomy, we use the Kelvin scale. And to derive that, we use what we're showing here, which is a constant volume gas thermometer. On the left-hand side, P, you have a reservoir of a gas, and that's in a bath or environment, which is what you want to measure. So as you heat up the bath, so the gas expands. It expands, and you have two reservoirs, two mercury reservoirs, A and B. As it expands, it pushes down the level of mercury in A. So when you've got the temperature in the bath that you want to measure, and everything settled down, you then alter the height of the mercury reservoir B, and you move it so that the level of the mercury in A is equal to the 0 on the scale. The temperature is then represented by the difference in height of the two mercury columns. If you then put more heat in, the gas expands more, push down on the mercury. You have to raise reservoir B even higher to get the level in A back to the 0 mark again. So H becomes greater as you increase the heat in the bath to maintain. We can then plot temperature against pressure. We know the temperature in the bath. We know the pressure from H. And what we find is there is a linear relationship, as shown in the graph. So there's no curve or anything, it's a straightforward linear relationship. So on the Kelvin scale, we need two fixed points again. We assign the first one to be the value of absolute 0. Okay, and 0 Kelvin, which we'll see in a moment is where it comes from, is actually minus 273.15 degrees centigrade. And so we'll see in a moment how we know that to be the case. The second point, we take the temperature of water at the triple point. The triple point is a unique situation with water where it exists simultaneously as solid, liquid, and a vapor or steam. It's quite low pressure, 0.006 atmospheres, and at a temperature just above the freezing point of water at normal atmospheric pressure, 0.01 degrees centigrade. So we assign the second fixed point, the triple point, as 273.16 Kelvin. This question of the triple point, you've got here what's called a phase diagram for water. And if you look there, you've got pressure in atmospheres on the left-hand side, 1 atmosphere as you move across, temperature along the bottom at 0 degrees, we see it changes from ice to water, which we know. And if we keep going along horizontally, at 100 degrees centigrade, it changes from water to water vapor or steam. Down below, we have the triple point. And you can see here, this is where ice, water, and water vapor all come together at the same point. And as you can see here, its atmosphere is 0.006 atmosphere, so it's almost a vacuum, but not quite. And the temperature is just 0.01 degrees above 0 centigrade, so 0.01 centigrade. So that's the triple point of water. So again, this question of absolute 0. We can take a series of measurements using our gas thermometer, measuring temperature against pressure, the temperature of the bath, the pressure represented by the height or the difference in height of the two mercury columns, and we can project the line back. Measurements are on the solid line. We can project the dotted line back to the axis until we reach 0 pressure. And we hit 0 pressure at minus 273.15 centigrade. And that is what we take as 0 Kelvin. And so the 0 Kelvin, absolute 0, is defined at that temperature where there is no pressure. What do we mean by pressure? If you've got a liquid, or a fluid, a liquid or a gas, you've got these molecules darting around inside the fluid, and they keep battering against the sides of the container. And we see that as pressure. The more heat we put in, for example, the greater the kinetic energy of the particles, the harder they hit the sides, hence we see greater pressure. So what we see as pressure in a container is simply the molecular motion of particles battering against the sides of the container. And at absolute zero, according to this, there is no pressure, so there is no kinetic energy. So absolute zero, no kinetic energy. There's no kinetic energy in the particles. There is no heat. There's no energy. There's nothing. If you try and get any colder than that, you're going to negative heat, negative kinetic energy, negative energy. It's difficult to understand how this can work. So it seems that, you know, once you get to 273.1 minus 273.15 centigrade, 0 Kelvin, we cannot go any colder because all molecular and atomic activity has ceased. There's nothing more to be done. There is no energy available. That is absolute zero. So just going back a moment, and you'll notice also that it's actually, this is where we get, so when we look at the cosmic microwave background radiation at 2.73 Kelvin, we can see that it's actually not absolute zero. I think many people assume the universe is at absolute zero, but it isn't. It's 2.73 degrees Kelvin above absolute zero. So it's pretty close, but not quite there. Okay, the first law of thermodynamics, we looked at the zeroth law. The first law says if you have a system of internal energy, the internal energy of the system is equal to the energy flow into the system minus the energy flow out of the system to do work. So you can't have a flow out of the system to do work without a flow in, which is why it is impossible to produce a perpetual motion machine. Okay, perpetual motion suggests it just keeps going without an input of energy, but that internal energy will get used up, which is used to do work on the system. Perpetual motion is impossible according to this. So we have here someone pumping a bike tire. That requires energy. Okay, we need to get the energy from somewhere. So the energy is the internal system of the Earth. In this case, someone eating food. So they're eating food. That provides internal energy to the body, which can then be used to pump up the wheel. And of course, oops, sorry, wrong way. The energy to grow the food has actually come from the sun. So the energy, you know, and it's so the energy has been used to produce the bread, the crops, and what have you, to actually make this. Is that a sandwich? I don't know. The Greeks don't do those, do they? To make the sandwich, and in fact also power any tools and equipment used as well to do whatever they used to make that sandwich. So you've got the internal energy of the person with the external input from the sun via the food, which can then be used to pump up the wheel on the bike. So the sun is pumping heat into the earth. We have what we call the greenhouse effect, which again you're all very familiar with. Obviously, if the earth doesn't radiate away as much heat as it receives, then it will start to get hotter, and that's of course what the greenhouse effect is all about. Having said that, of course, we need to be a bit careful here. You may have not heard of the Goldilocks zone around a star. That's the Goldilocks zone, is that area, that distance from the star where the temperature for life is not too hot, not too cold, it's just right. And it's really normal, as far as we're concerned, it's that distance from the star where we have liquid water on the planet. The problem we have is that the average temperature of the Earth, I think, is about 14 centigrade, because we have a greenhouse effect. If we get rid of the greenhouse effect, the average temperature of the Earth is actually, I think, -1 centigrade. We're actually just outside the Goldilocks zone, apparently. It's only the greenhouse effect that allows us to have life. So when we try and deal with the greenhouse effect, we've got to be a little careful. We don't want to get rid of too much of it. The second law of thermodynamics, we've talked about this already, it's not possible to transfer heat from a colder to a hotter body. It's obvious when we think about it. Well, not obvious, actually. You can't prove it. You can demonstrate it, but you can't prove it. And if you can prove it the other way, great, you make a fortune. Some people will say, A refrigerator will do that, transfers from cold to hot. It transfers heat from the cold refrigerator to the hot room, but it's using extra input of energy from the compressor. The compressor's plugged into the mains. It's using electrical energy to do it. So it doesn't violate Clausius's statement. The statement in the second law is a little different. No process is possible for which the sole result is a conversion of thermal energy into mechanical energy. So what he's saying is that there will be some loss along the way. You can convert some of the heat into mechanical energy, but again, looking at the car engine, steam or internal combustion engines, steam engines as well, we're taking heat, converting it into work, but we don't just get work. There's a lot of heat lost from these engines, exhausts, cooling systems, bearings, and so on, in the case of car transmissions and so on. There's a lot of heat lost from the vehicle. This brings us to the concept of the heat engine. So we have a hot reservoir and a cold reservoir, the engine in between, and the engine capable of doing work. And the engine works from the hot and cold reservoirs. Okay. So the engine takes heat from the hot reservoir. This could be, say, a car engine. So it's got the stored energy in petrol. It uses the petrol to produce the hot reservoir. It uses the hot reservoir then from the combustion of the fuel to power the engine, but it also rejects some heat through into the cold reservoir, which is the atmosphere. And again, it does this through heat from the bearings, from the brakes, the radiator, the exhaust. If you don't believe me that an engine rejects heat, run your car engine for a few minutes, then grab hold of the exhaust manifold. When you stop screaming, take yourself down to casualty. It hurts. I've done it. Even the back of the car, feel the exhaust. It's actually warm. It's above ambient temperature normally. So the engine's rejecting quite a lot of heat. And this is one of the problems with it, actually. We can't use that rejected heat to pump back into the engine. It's not a reversible process. It is irreversible. We can take from the hot reservoir to the cold reservoir through the engine, but we can't use the heat that's rejected to power the engine again. It's still there as energy, but it can't be used to do work. The solar system is a heat engine. We have stored energy in the sun in the form of atoms. It produces the hot side of the sun by means of nuclear fusion. This is transmitted to the Earth. The Earth is effectively a heat engine because most of the functions that take most things that happen on the Earth are as a result of heat from the sun, one way or another, even if it's not directly. And then, as we talked about just now, we then try and reject heat from the Earth to the cold side, which is space around the Earth. If we don't, the Earth starts to heat up, which is again this question of global warming and greenhouse effect and so on. So the solar system is basically a heat engine. It's not much different actually to a car engine. It works a little differently, but the principles in thermodynamics are really the same. This question of catching heat from the sun, actually, when you think about it, we're a tiny little planet and a massive sun. The great majority of heat passes us by. We lose most of the energy from the sun. It goes elsewhere. We don't see it. Back in the 1950s, a guy called Freeman Dyson came up with some ideas about how to deal with this. The first of these was a Dyson swarm. What you've got here is a whole series of habitats or biospheres in orbit around the star. So it's gathering heat in a big ring around the star rather than just a single planet. You can extend this. This is the Dyson swarm, again, all these biospheres and arranged in a series of rings around the star. Or you can have a bubble where they're arranged in a different orientation. The final one, perhaps the most interesting, is the Dyson sphere. And here you have a complete sphere surrounding the star. If you're doing this with the solar system, for example, I would suggest that sphere has a diameter, a radius of 93 million miles. To put at the edge of it, with the sphere in the same orbit as the Earth is. You have an issue here, of course, that you need to release heat from the sphere, otherwise it will overheat. But look at the amount of living space you get on the inside. You get an enormous amount of living space. The interesting point as well is this can be used as a way of finding ET. If you can go back through the record and find a star that was there one year, then several years later had disappeared, it does suggest there might be a Dyson sphere built around it. The check, of course, would be then to take an infrared image, and if you can see the star in infrared, but not invisible light, it does suggest, there are probably other explanations, but it does suggest that someone may have built a Dyson sphere around it. The problem we have here then, of course, is that if they are so advanced they can build a Dyson sphere, this sphere around a star 93 million miles radius, do we really want to make them know we're here? They're so far advanced, we can't even engineer on a planetary scale. They're engineering on a stellar scale. They're so far advanced from us that we really want to keep quiet, I think, at that point. Again, back in the 70s, actually, Larry Niven wrote a book called Ringworld. And you can see here another way of trapping the heat from the star. He's got a ring around the star. Again, if this was the solar system, that ring would have a radius of 93 million miles. It's got sidewalls on it to contain the atmosphere so it doesn't spill over. And you've got cooling fins on the underside, which you can see on the left-hand picture as well. On the right-hand picture, you've got, again, another drawing of the picture of the ring world. And you've got an inner ring as well, consisting of sheets of material held together with cables. So you've got material gap. And this revolves as well around the star. And it gives you night and day. You get periods of shadow followed by periods of light. So something to look forward to, perhaps. One thing you may have heard of is entropy. And a lot of people have struggled with this concept. And they start talking about it in terms of water disorder and how teenagers' rooms get untidy and all the rest of it. It's rubbish, forget it. Okay. Entropy is very simple, and I've already mentioned it in passing. Entropy is the measure of the energy that is not available for work. So if we take this heat engine we've looked at before as a closed system, and we have the hot reservoir producing the heat to drive the engine, which is rejecting heat into the cold reservoir, but it's a closed system, so it's containing the heat within the system. But the heat in the cold reservoir, as I've said, is no longer available to do work. You can't get heat from the flow the other way, only from hot to cold. So the heat is still there, but it can't use it to do work. And so this heat represents entropy. And the more heat we reject, the greater the rise in entropy. Entropy represents the energy no longer available for work. It's as simple as that. In terms of the universe, if the process is reversible, then the entropy is constant. But entropy, if you have an irreversible process like the heat engine, then the entropy will increase, and so the entropy of the universe increases. The entropy of the universe never decreases. Whatever we do increases the entropy of the universe, because we're putting out, I mean, even us, we're sitting here doing nothing, we're still putting out heat from our bodies, which is no longer used for anything else. And so the entropy of the universe is still increasing. When we talk about entropy, we're talking about thermal equilibrium. As the system approaches equilibrium, thermal equilibrium, so its entropy increases. When it's at an even temperature throughout, entropy is at a maximum. As you move away from equilibrium, so entropy decreases. I mentioned this idea of disorder just now. It comes from statistical mechanics. I'm not going there today. I'm not going there ever, actually. Just understand it is a measure of the energy that is no longer available to do useful work. It's energy that's typically been rejected by the system. The universe is a big irreversible system. You can't wind it back. It only goes one way. And it's made up of a lot smaller irreversible systems. And because it's irreversible, the entropy of the universe always increases. And we will reach a point at some point in the future where the entropy of the universe is at a maximum. This means the universe is in thermal equilibrium. There is an even temperature, there's no temperature difference anywhere in the universe. And because there's no temperature difference, no work can be done. Remember the universe, the solar system, such like heat engine, no difference in temperature, no work can be done. Entropy is at a maximum. So what we can look forward to is the heat death of the universe. And with Marty's impression of the heat death, it's sometime in the future, all the stars have gone out by now, so they're no longer generating heat. We get some energy from supermassive black holes, but even they will decay maybe 10 to 100 years. So entropy can keep increasing until that time. Even protons, the building block of atoms, have a half-life and they will decay as well. We are talking hundreds of thousands of billions of years, so don't make it in your diary yet. But we can look forward to a future of the universe, so-called dark era, when it's basically a mixture of gas and particles. Matter has disappeared from it by this stage. It is at an even temperature throughout, so there's no activity. Entropy will be at a maximum, it will cease, and the universe will have achieved the heat death. And that is how it will remain. Some people think the heat death has already occurred. They look at the universe and they see mostly something at a fairly even temperature, 2.73 Kelvin. A few, I say a few, several hundred billion really, galaxies, which are islands of heat and light. But the bulk of the universe is actually pretty cold by now, so they may suggest the heat death's already occurred. I think to finish, we'll look at an alternative view, the Garfield way. And I think finally, a sentiment many people will identify with. Are there any questions?